All right, so we're going to continue our discussion on shell balances. And just as a quick recap, so we are dealing with microscopic momentum transport right now. First, we discussed viscosity and what are the origins of viscosity microscopically. And we are now working on, then after that, we generalized our concept of viscosity to a stress tensor, and also looked at all of the possible mechanisms that could actually change momentum. And we basically formed one big thing called combined stress tensor that has all of the pieces in it. And then we're now working on actually applying that knowledge and solving for some shell balances. And one of the key concepts in generalizing this stresses was generalizing Newton's law to most sort of general 3D situation. So for that, we defined a stress tensor, tau. So these two underlying things are denoting a tensor, which is minus mu gradient of velocity, velocity being a vector, gradient of velocity is a tensor itself, and it has it has 9 components, plus the transpose of that tensor, and plus the coefficient, some general coefficient times divergence of V. Divergence of V really measures how much has the element changed in its volume. Do I have any compressible effects? And if I have an incompressible fluid, that contribution is going to be 0. And then ultimately, that's time. So divergence of a vector is a scalar. So that's just a number. Divergence of vector is dvx dx plus dvy dy plus dvz dz. So it's a scalar. And I multiply that scalar times identity matrix, which gives me stress tensor. So basically, these being tensors, if I actually want to compute or work with anything, I have to figure out what are the components of it. So basically, Pij in general will have, so that my combined stress will have this tau ij, which is the viscous component. And those are the stresses that are in the above matrix, plus pressure, this is thermodynamic pressure, and plus rho, vi, vj, this is the convective component, quite literally the moment the momentum that just flows into my control volume. Okay, so now we devised a method for problem solving. In the most simple case, we're actually going to look at the steady state solutions. Okay, so in a steady state case, there is no accumulated momentum change. Okay, so that part is 0. So 0 equals to whatever momentum comes into my element, which I'm calling a shell, minus whatever comes out. I can also, if you're used to integral forms in fluid mechanics, you basically integrate over the boundary and see what the net in or out is. Okay, so this is my net. And then I could also have some external forces changing my momentum, so I basically separate that out. So we basically find a little shell in the geometry. The shape of the shell will be dictated by the shape of whatever it is that I'm solving in. And my coordinate system will be dictated by that shape as well. So most simple one is the Cartesian coordinate system, but then we're also today going to have cylindrical and later on spherical. So these curved coordinate systems are a little, well, troublesome to deal with when we're solving the problems. So just remember always to just look up the formulas whenever we're looking at the stress tensor or so forth. It's just easier to look up until you become really confident that you know what those terms are. So basically we will apply the balance on this, and that's where we're actually having that combined momentum helps. So we're going to basically just state the balance for that combined momentum, add any external forces, and then once I get the equation, I'm going to let that element or shell shrink. And that's going to give me partial differential equation. Could I just give you partial differential equation to begin with, and we can solve the problem? Yeah, well, boundary conditions you always have to figure out. So yes, and I'm actually going to give you, that's basically our chapter 3 coming afterwards. However, in many cases, so when you have the most general equation, it can be quite burdensome, okay? And you don't get to visualize and analyze the problem properly. So shell balances actually give you a little more hands-on in understanding the physical problem. That's one way, one reason to use shell balances. Second one is that actually as you're putting the shell balance together, I'm calling that like an onion, you're actually working with a layer by layer of your problem, and it's often actually easier to solve the PDE that way. Whereas when I have this humongous nonlinear PDE that I'm trying to solve and I throw in all of the possible partial derivatives, it's going to be hard to solve unless I'm actually having a numerical simulator on my hand. Okay? So sometimes having just a PDE that I could serve you doesn't really help me in solving the problem. So shell balances, especially for steady state, are probably a better way to actually find the way to solve your differential equation. And when you're dealing with step by step, then you're also thinking through the problem a little more, what's coming in, what's coming out, things like those. And that kind of gives you a better physical understanding of the problem. So ultimately, you will be the judge. Okay? So in the test, I might actually require do the shell balance. Or if I don't require, you can pick. And as you're solving problems, you will figure out what actually comes to you easily, or what it is that you're better at. Okay? So if you like just throwing a PDE on the paper and then working out what to cancel from that PDE, be my guest. Okay? So that's in terms of problem solving. So you might have already had transport phenomena before or fluid mechanics, and you're used to a certain way. This might be a slightly different way than what you learned before. Again, it's always good to see different ways to solve problems, and then in the end you figure out what works better for you. So let's just quickly summarize what did we do for our first example. Our first example is one of the simplest examples, partly because the geometry is so simple. Okay? So I'm working in a Cartesian coordinate system, very thin flow or liquid coating that is flowing down a relatively gentle slope. I placed the coordinate system where I called x and z these two directions that are the main directions we're solving for. Y is going into my paper, and everything is same in y, so I can kind of throw it away. It cancels out. And basically, we neglected whatever acceleration exists in z direction, so that would give me a z dependence on my velocity. So I'm assuming that the only dependence that velocity has is that on this x direction. So at every point right here in a steady state, I have a constant, the same velocity, right? And all of these points have the same velocity as well. So my velocity profile looks like this for my entire geometry. And then at the same time, I actually have to then assume that my pressure is a function of x as well, because if pressure had z dependence, so would b. Okay, so velocity and pressure are always kind of entangled together. So once you make an assumption, you have to make sure that you're making consistent assumptions, okay, when you're simplifying problems. So we are basically then, once we put that all in, we did a shell balance. And one important thing somebody already noted is that we have to always know boundary conditions. And quite frankly, if anything is going to give you pain, those are boundary conditions. So near the boundary, if you even have a partial differential equation, it's valid at a point that is sort of internal point of your geometry. When you're close to the boundary, your partial differential or computing derivatives are valid only up until that boundary, but not across the boundary. So this is where you have to place your boundary conditions, and you have to know the values, and that shapes your solution in a great way. Okay? So it's whether you have open boundary or a closed boundary will really shape this flow. So think about it this way. Here I have air, and therefore I have only a half parabola. Okay? if I had a solid wall, I would have a full parabola. And that would really change my profile, okay? And overall, the flux going through. So it's a major, putting any kind of wall as a boundary will shape your solution and ultimately really change the flux going through. Equation in itself didn't change at all. It's just the boundary conditions that can change. So just from that, you can actually see that boundary conditions can really influence your solution and can also throw a wrench in finding a solution, okay? Depending on how difficult this boundary condition is to implement. So what we assume is a very common one, that there is no slip on the solid wall, so my velocity is that old wall, and in this case, wall is not moving, so velocity will be 0. So an easy variation of this problem would be, well, what if I actually have a moving wall? How would a wall could move up or down? How would my profile actually change? And then on top we have air, and we say it's a 0 shear stress. That comes from continuity of shear stress across this boundary. And since I have air and liquid, presumably air is much, much, much less viscous than this is, and often an order or even 2 orders of magnitude difference. And because of that, when I have mu multiplying my partial derivative in velocity, that mu will cancel out whatever I have, so that's what's creating 0 shear stress on one side, and because of the continuity, I have to have that on the other side as well. Yes?
What part of our solution makes it specific to only euclidean geometry?
The fact that we're actually assuming that you have this orderly laminar flow. Okay. So any kind of thicker flow, it's going to be extremely hard to avoid any kind of ripple effects and also acceleration down. And in a lot of applications of interest, it's this thin layers that are of interest as well. They're never going to form as very thick layers because gravity will pull them in a different direction. So basically, this is one of the most common boundary conditions. So today, I'm going to put a little more note on boundary conditions, but let me just finish this example. So we will apply Z momentum balance, and after balancing out all of the contributions, we got this parabolic profile, so that's precisely the solution here. So one important thing to note is that velocity is minimized at the solid wall. Shear stress is maximized in absolute value at the solid wall. Shear stress is 0 at this boundary, and that's where velocity is maximum. So they kind of have the reverse behavior. Okay. On your own, you can actually go and balance X momentum, and that will actually give you pressure, P of X. Okay. So that's, you can repeat the entire example, and I'm going to actually throw in a warning here. Read whenever on the exam. So I had on one of the exams in the past, I gave this problem and I said balance X momentum. Despite of me putting it in bold, saying X momentum, 25% of the class solved for Z momentum because that's what we did in class. So just because we normally don't balance X momentum for one reason or another, don't assume that I'm gonna. And then everything else in that problem fell apart because nothing made sense afterwards. So all the following up questions didn't make sense because people did not. And funny things happen when you actually get into this mode. Oh, let me just solve. Because I think everybody's like, oh, I know how to do this. And boom, 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 boom. Right? And then you just go and solve it. Some people started with X momentum and halfway through flipped those PRZ, not PRZ, PXZ, PZX kind of thing, flipped them over to force the Z momentum balance. It was hilarious to watch. Do this exercise. Go do it and see how different it is, and try not to flip things zx, xz, okay, and actually solve the problem for pressure. Okay? Because everybody was super upset that they didn't get velocity distribution as a result. Well, there is no velocity in x direction, so you're not going to, if you're balancing that momentum, there's not much to balance, you're really just balancing pressures. But your velocity, we already assumed velocity in x is 0, so I don't need to solve for it, right? I assumed it's 0. But that doesn't mean that balancing the momentum is not going to give you any information about the problem. Okay? So just be aware of that. Okay? Don't repeat that. So then, once we have the distribution, we are interested in finding what is the maximum velocity, volumetric flow rate, average velocity, and also Reynolds number of the flow. I'm going to comment on it in a second. So essentially, often I have both, I might be in the lab doing experiments, and if I'm actually doing this computation, I want to give myself the idea of what is the realistic expectations of the velocities. So if I'm seeing velocity that is much larger, in the lab while trying to ensure that things don't have ripple effects and so forth, this actually gives me some idea of what velocities I should be working with. So always look at experiments and theory as complementing each other. They're never, one is never fully enough for understanding the problem. And especially in this case with fluids, with this governing equations are so nonlinear, and we know that things can have, you have to know how is your fluid behaving. Is it laminar, is it turbulent, before you're actually solving the problem. So there's no magic wand that can just solve the problem for you. You kind of have to work with it. Okay? So here are the quantities. So if you actually just go and plug things in, so we see that the velocity was maximum at that air interface. That's my V0. If I want to know the volumetric flux, I would take the velocity profile and integrate it over that side, which is a two-dimensional thing. Okay, and I would actually go into y direction as well to get the full volumetric profile. If I want to find out the average of velocity, I would take that volumetric flux and divide it by the area I was actually integrating over, okay, which is in this, this. And then Reynolds number is something that characterizes flow. Reynolds number, and we're going to look into it a little more later once we actually look at the equation of motion. So Reynolds number, I have to compare Reynolds numbers for shapes or geometries that are similar. So I cannot look at the Reynolds number for flow around a sphere and compare it to the Reynolds number of this thin film, okay? Because those are two different geometries. So basically my geometries have to be similar. And once they're similar, conceptually Reynolds number is some velocity that is characteristic for the flow, okay? Rho, which is density of the fluid, some length that is characteristic for the flow, and divided by viscosity. Which particular velocity? Am I going to take V max or V average or something like that? That's up to community, research community to decide. And typically there is some historical velocity that is taken, okay? So in this particular case, for the thin slit, it's this average velocity, okay? Which particular length to take, that also is up for discussion. And historically, different types of lengths are taken for different geometries. So if I have a bowl, I'm most likely going to go for the diameter of that bowl, right? But somebody could go with the radius, okay? So take absolute value of Reynolds number, you can always take it with a grain of salt. Like it's really, what you're looking at is order of magnitude that matters, okay? So times 2, times 3, times 4, that's not all that important. What's important is the order of magnitude, okay? Because there are certain choices that you can make. And you have to look them up in literature to see what have people traditionally been taking for what type of flow. And in this type, they were taking 4. And I'm pretty sure in some normalization, I didn't look it up, but for some normalization in the past, it made sense to put 4 in there, okay? So that something is normalized or equal to 1 or in some case. So basically for every different flow, you're going to have slightly different Reynolds numbers. In this particular case, also for every different situation, you're going to have this borderline Reynolds number that gives you laminar to turbulent crossover. And in this particular case, it's 20. We will see for tube it's 2100 or for slip. Okay? So these numbers they just have to be kind of memorized and known. So essentially, if I'm in the lab, this also tells me what I should be enforcing in order to have a laminar flow. All right. So, yeah, okay, we'll comment on it a little more. So let's just look at the generalized boundary conditions. If I have fluid and solid, we typically assume that there is no mass transfer through the boundary. So that means that if I take velocity of the fluid and project it onto the normal to this, so this is my normal to the solid. If I project it, it's the same as this normal velocity of the solid, which in many cases is 0. Okay. So normal velocity components match, and if the solid is static, then that's equal to 0. Okay. We often also take no slip, which means that tangential velocity components, so if this is my tangential flow, and in 3 directions I'm of course going to have 2 tangential directions, then tangential velocity components of fluid and solid are also equal if I have no slip. And slip means that tangential velocity is proportional to shear stress at that boundary. Okay? And there's this coefficient, which is often something that I have to tweak, which is called slip length. Okay? You will actually have a homework problem based on this. So there are various ways to define the slip length. In this case, you're saying, okay, there's this beta that is times the shear stress on that boundary. You could also view it as, okay, so my velocity is not 0 on the boundary, but it's somewhere inside the boundary where it's actually going to go 0 formally, even though I don't have fluid there. Okay? So that slip length could be actually thought of as that length of how long inwards do you need to take to actually zero out that velocity profile. Okay? It's not precisely the same as this beta, but to the first order, those 2 things match. Okay? So my point is that these are modeling solutions. Defining this beta, again, takes some measurements in the lab to actually figure out what works really the best, but typically you come in with certain assumptions. Okay? And we could also, of course, have porous boundary. We are working with porous media a lot. And I might have a microporous grain, so my grain might actually have some porosity to it, for instance, because of dissolution. Okay. And then you actually need to specify the constant flux on the boundary. This is often for those of you who are going to work in fractured formations or modeling fractured flow. Typically, you have a similar situation near the fracture. You have rock matrix, and you actually have to specify what is the transfer across that boundary for all of the fluids involved. And that's not necessarily easy, and of course affects your overall solution a lot. And those are certain assumptions that you often have to simply make. Okay? So beware of the boundary conditions. Again, they can change your solution a lot. All right. If I have fluid-fluid situation, okay, then typically we will assume no mass transfer, but there it could be. You could be actually working on a research problem that does have mass transfer, but we will assume that there is no mass transfer. So my velocities, and let's say that I have fluid 1 and fluid 2, are continuous across that boundary. So both normal and tangential projection of these velocities are the same. No slip assumes continuity of tangential velocities. This is this. And we will also assume continuity of shear stress. So for the most part, everything is continuous across the boundary. I could have different velocity profiles into different fluids, but they have to match on that boundary, and also not just velocities, but their derivatives, because shear stress depends on derivatives times the viscosity, they have to match as well. Okay. So I know that shear stress is some combination of coefficients times derivatives of my velocity. Okay. I could have a jump condition for the normal component of stress. So if I take the total molecular stress, okay, I could have a jump, and basically the curved interface, or the way interface curves, balances out that jump in stresses. So the more curved I am, that's called capillary pressure across the so basically fluid-fluid interface is capable of supporting jump in pressure across that boundary, and it curves in response to that. So this is something that you will mention a lot in petrophysics. Here, for the most part, we're going to be dealing with single-phase flow, so we're not going to look into this, but this is something for your information. Also, if I actually have gradients in surface tension in tangential direction, okay? So for cases where my surface tension is not constant, but it's changing, okay? I might have that, so my stresses might be able to support that as well. Okay. Again, for the most applications, you will actually have a constant surface tension, or you will assume the surface tension between the fluids is constant. This is just the most general case. Again, for the most part, we will ignore this, or we will assume that the radius of this tube is so large that basically whatever curvature it has, I can ignore, okay? So for any kind of large tube, this jump can be ignored. So if I had like a tank, I'm not gonna look at the capillary pressure across, because relative to all of the other pressures, it's minimal, okay? And again, in most applications, this surface gradient of interfacial tension is 0, but if it's not, then you have all kinds of fun stuff going on. Is that Marangoni effect, I believe? When you actually have a gradient in surface tensions, and that can actually do fun stuff to your interfaces. All right, so this is just general comment on boundary conditions before we actually now continue with solving the problems. So let's get going. So now we will actually have the second example. And that is going to be laminar flow, steady state, laminar flow of a Newtonian fluid. Fluid in cylindrical tube. So in terms of fluids and situation, the flow regime, everything is the same as the thin film, but what's changing is my geometry. Okay? And that will have a major change in how we actually solve the problem. So what is my tube? My tube has radius r, and length L. And here at the beginning, I have some pressure P0, pressure PL. And I am in the cylindrical coordinate system. So I have R, theta, and Z. So theta is changing theta direction, right? Now we will assume that we only have z velocity down this tube, okay? So assumption, the only non-zero velocity is vz. And that velocity, it doesn't really, so if this is my, for instance, this is my theta 1, or this is my theta 2. So it doesn't really depend on theta itself, right? It really depends on how far I am from the center of the tube. So it's really a function of Vz of r. Okay. And the other two velocities, so I don't have any cross flow, so I don't have any Vr or V theta velocity. Theta would be going around, right? So V theta V r are 0. All right, so we will basically ignore the theta component because we think that every kind of theta cross section I look at, I see the same thing, right? So I can basically ignore that. Now, what is my shell here? Let's draw the shell. I'm gonna make it a little larger. My shell has thickness delta z. Okay. And also in r direction it has thickness, and I can only draw eggs apparently. I don't know how to draw. Okay. So I also have, let me change the color here, thickness delta r. In r direction. And one interesting thing about this is when I look at the areas that I have involved, okay? So I have areas across which my momentum could enter or exit, okay, that I had to integrate over. When I look at this area, so area on top, it's the same, I'm gonna call this area, let's say AZ. Oops, AZ. This area is the same on top and the bottom of this shell, and it's equal to what? This area here. Larger circle minus smaller circle, right? So if I assume that my larger circle, so this is some r and this is r plus delta r, we are always working like this: x plus delta x, y plus delta y, z plus delta z, r plus delta r. So those are my boundaries typically, okay? So it's gonna be the area of the larger circle minus area of the smaller circle. So that's when I do that, I'm pretty certain you know how to do that. This is what I'm left with. And we're going to simplify it immediately. If delta r is going to be small, delta r squared is much smaller, order of magnitude smaller. So I'm going to actually just immediately approximate this with 2p r delta r. So I'm just basically saying this is too small. So approximately 0. Okay. The other area element, so this AZ evaluated as Z is the same as AZ evaluated as Z plus delta Z. No matter which Z I look at, I have the same area. Okay? That is not so for my R direction or area orthogonal to R direction, right? So if I have a radial vector, this curved area is basically the area that I'm looking at in cylindrical coordinate system. And this curved area is changing. Larger the r, larger the area. So if I'm enforcing constant flux, okay, then basically I'm going to have, if I actually have just a constant volumetric flux going out of a source, for instance, you have a well bore, that could be a source, you're injecting something, right? You're going to actually have less and less fluid going over a certain constant piece of area further you are out, because you have this constant volume that keeps spreading over larger area. So when you look at it per area, it's going to really change in a way from the well bore. And that's a big deal, because if you're trying to flush something, you don't have as much power, okay, far away from the boundary. So you're not going to be as effective in displacing oil. We're typically interested in displacing oil, right? So you're less and less effective away from the well bore, and that's a problem. Well, how do we compute what it is? So here, this little area, I'm going to call it AR. Okay. So this AR is basically, it has height delta Z, and the perimeter down there is 2RP, right? So it's a cylindrical area. But that's evaluated at this point R. If I am evaluating it at R plus delta R, I'm going to have delta Z 2, and my radius has changed, so it's R plus delta RP. So note that, like, when I say AR, I'm just saying that's general name for this radial area, and I'm evaluating it at point R and point R plus delta R, and depending on the point that I evaluate it at, I have to take that radius into account. So changes with radial distance. Now, if I'm actually balancing things in these things, we said we have to look at the combined momentum, and we also have to, at the end, add any outside external forces. So now when I'm looking at these areas, okay, let's say that I'm interested in Z momentum balance, okay? So what is going to tell me how does Z momentum changes across Z or Z plane or any area orthogonal to Z direction? What part of my combined, so I had that big vector phi, not vector, the big tensor, right? So I'm interested in components of phi that are describing my Z momentum transfer. What are those? Phi ZZ, phi RZ, phi theta Z, right? There's Z momentum across theta, Z momentum across R, Z momentum across Z. Okay? I can look at it actually as a vector, if you will. So basically I can look at it as a phi Z. It's a vector, right? Okay. Now I know that phi is, it has the pressure component, it has the viscous stress component. Those are my total molecular stresses. And then it has that rho VV, which is stuff flowing in through the boundary, convective component. Okay. So then likewise, my phi RZ is going to, I'm not going to look at phi theta Z because I'm ignoring theta altogether. Nothing is changing in theta. And I don't have a surface. I don't have a theta surface in my little shell. The way I drew it, there's no theta surfaces, right? Theta planes. So my phi RZ is what? Do I have the pressure component? Shear? No. So I have only tau RZ plus rho VR VZ. Good news is we assumed VR is 0. So that is equal to tau RZ. Now what is phi ZZ? I actually have pressure P plus tau ZZ plus rho VZ squared. So now we know kind of what everything else is. I'm going to work with tau RZ when we get to actually solving for velocity profile. Let's actually do the balance. So what is my balance? My balance is rate of momentum coming in through the top surface minus rate of momentum coming out through the bottom surface. Okay? What's coming in through the top surface? Which momentum describes Z momentum coming in through Z plane? Phi ZZ. And the only thing that I have to do to actually see how much is coming in, I have to multiply it by area, because momentum, it's, right? So shear stress itself is not multiplied by area. And then I will have to figure out, okay, how much it's coming in through this R boundary here, and how much is coming out through the boundary, R boundary on the other side. Do you see me? You don't see me moving? I'm pointing to myself big time here. All right. So basically, I have this top boundary stuff coming in, phi ZZ multiplied by area, and on the other end, stuff coming out, phi ZZ multiplied by area, right? And then I have stuff coming in through this boundary. This is my phi RZ, okay? At this evaluated at R times the area that is actually relevant here. And stuff coming out is phi RZ, but multiplied with a different area, okay? And that's coming out on this boundary. So again, stuff coming in, out, in R direction, okay? So let's write that down. So that's basically phi ZZ evaluated at Z times AZ evaluated at Z. Or I can just refer to that as AZ plus delta Z, AZ because it's the same anyway. Minus what's coming out is phi ZZ evaluated at Z plus delta Z times AZ. Note that this is the same as AZ plus delta Z because the areas are the same. And then we look at stuff coming in at, that's phi RZ evaluated R times AR minus, I'm going to call this AR plus delta R. I should have done that to begin with. Phi RZ evaluated at R plus delta R times AR plus delta R. So that is the balance of the momentum. I have no other surfaces to go in or out from. And now I just need to add external forces. What is the external force here? Standard one, gravity. So, rho G. I just have to also need to multiply it by volume, right? So my volume is plus rho G. It's basically this AZ times delta Z, right? Area AZ times delta Z. So this is my external body force. All right. So let's now put things in, or maybe I'll just stop here because I'm going to have to go through it anyway. So this is going to be where we stop today. And we will form this solution next time.